Question 13 of the 2026 AIME 2 is asking for us to call finite self-integers s and t cousins if s and t have the same numbers of elements, s and t are disjoint, and the elements of s can be paired with the elements of t, so that the elements in each pair differ by exactly 1. For example, 1, 2, 5 and 0, 3, 4 are cousins. Suppose that the set S has exactly 4, 0, 4, 0 cousins. Find the least number of elements that a set S can have. Now, this question is quite straightforward. So we're told two sets S and T are cousins if they meet these criteria, and that it has exactly 4,040 cousins, and we want to find the minimum size of S. So now we have to understand the pairing mechanism first. So take a single number S like this. Now it can only pair with S minus 1 or S plus 1, right? So each element gives two choices here. If all elements behave independently and absolute value of S equals n, we will get 2 to the power of n cousins. But it can't be, because if two elements of S differ by 2, their pairing choices interfere. For example, if, in this case, S equals 1, 1 can pairs with 0 or 2. 3 pairs with 2 or 4. But 2 cannot pair with both 1 and 3. So obviously this won't work. Now, we need to group the elements. So suppose if we group elements of S into blocks where each element differs by 2 to the next. An example of this can be A plus 2, A plus 4, A plus 6. Now, we can call the length of X. So, a block of length X contributes exactly X plus 1 valid pairings configurations, right? So we know that like each new element adds one extra configuration because it shifts the possible matching boundaries. So a block of one element gives you two cousins. So if X equals 1, a block of 2 gives 3, a block of 3 gives 4, so on, so on. So the pattern is X becomes X plus 1, right? So now, if blocks are separated by more than 2, they don't interfere. So their counts multiply. If you have blocks of length x1, x2, x3, then the total cousins will be x1 plus 1 times x2 plus 1 times x3 plus 1. Now, we want this product to equal 4040. So let's factor 4040, right? So the prime factorization would be 2 to the power of 3 times 5 times 101. Now, we want to minimize the total elements, since this question is asking for the least value of S, right? So we want x1 plus 1 times x2 plus 1 to be equal to 4040. To minimize total elements, x1 plus x2 plus ... We'll take the prime factors directly. So 8, 5, 1, 0, 1. Now, x1 plus 1 equals 8, so x1 will equal 7. x2 plus 1 equals 5, so x2 equals 4. x3 plus 1 equals 101. x3 will therefore equal to 100. Now, total elements are 7 plus 4 plus 100, which is the least possible value, right? But that's not the answer. This would equal 111 because 8 can be broken into 4 and 2. 4, and 2. Now, since smaller factors reduces total x sum, a better factorization of 4040 would be 2 times 2 times 2 times 5 times 101. So now, x plus 1 equals 2, therefore x equals 1. If x equals 1, we get 3 1-element blocks, 1 4-element block, and 1 100-element block. So 1 plus 1 plus 1 plus 4 plus 100. So the final answer is 107. And that's the minimum value that it could get.